So this video we are going to understand the conduction rate equation or Fourier's law equation in multiple or different coordinate systems. So we have the conduction rate equation known to us, which is Qx is equal to minus Ka dt by dx. So this was for one dimension when I am using d. So dt by dx means this is the finite differential and the finite or complete differential. But when I need to use multiple dimensions, then I need to use partial differential. So when I define my heat transfer, or when I need to use this equation in multiple directions, then I need to use partial differentials, and so this can be written as this in terms of flux minus K dt by dx. The small x subscript x came because I am taking the differential in x direction. So the differential in y direction will give me the flux in y direction, etc. Now, as I said earlier, the flux is vector. So what is the direction? It's the direction of x. That means generally the direction of heat transfer will be normal to a surface of constant temperature. That means if I have a surface which has a constant temperature T1 and another surface, or it may not be present, but from here, from this surface, always the heat transfer will be perpendicular to it. That is in the n cap direction. That is the normal direction to the area. So this is the area, actual area, and the n cap will be the n cap direction, that will be the normal direction. So I can always write it as a generalized form minus K dt by dn, that is in the n direction. This is simple. This thing can be used for x, y, z, etc. Now let's look at the formulas for three different coordinate systems which we studied earlier. So the rectangular coordinate system uses x, y, z. Cylindrical coordinate system uses r, phi, z. And spherical coordinate system uses r, phi, theta. Okay. So the formulas are given over here. Qx, the flux in x direction, the flux in y direction, flux in z direction, these are very simple. Minus K del T differential, partial differential of temperature in x direction, partial differential of temperature in y, partial differential of temperature in z direction. So the minus sign is taken into account so as to use the temperature, the partial differentials of temperature from higher to lower side. So if T1 and T2 were there, earlier I used to take T2 minus T1, but now from now on we will take T1 minus T2 as the partial differentials. So that's why we are taking minus sign. For cylindrical coordinates, we'll have the flux in r, flux in theta, and flux in phi and flux in z direction, and the partial differentials are like this. Remember, we have an extra factor over here which looks like this. We have 1 over r in the phi direction. Now in the spherical we have r, phi and theta. So flux in r, flux in phi and flux in theta, the formulas are given over here. The special note we need to take is over here with phi we have 1 over r sine theta, and with theta we have 1 over r. So this phi factor, the factor which we had in phi for cylindrical, has come to theta in spherical. So that's the difference. That's all we have. From next we'll start using this thing. So I'll give you a general steps on which how to solve a heat transfer problem, and then we'll go into more details of this in a step-by-step process for different types of classification of problems based on steady state or 1 dimension, 2 dimension, 3 dimension, heat generation is involved or not, if we have cylindrical coordinates, spherical coordinates, we have a wall, etc. So from next we'll start solving problems actually. Thank you.